First of all, let me open my camera and then let me open my screen to share with you. Moment. I think this is the one. All right. So, hi everybody. It's Celal Hakan Canbaz. I'm a petroleum engineer who has a master's degree from Istanbul Technical University, and then I'm doing my PhD in energy. Energy. I worked in the industry for about 13-14 years. Currently in Middle East in different locations. Now this will be a 4-week course, and the first week will be regarding on the introduction to reservoir and geology. Will include the basics related to reservoir and geology topics in general. In the second week, we will talk about fluid properties and phase diagrams, which will be useful for the third week topic. The third week topic will be multi-phase flow meters. I will try to introduce the flow meters which are available in the market and their advantage, disadvantage, and what's the multi-phase metering concept and how it is used in the industry, to description of which parameters like this. And in the fourth week, it will be a little bit different topic, which is not also care about the industry too much as far as I see. It will be perforation techniques related to perforation guns, the design of perforation, the loads that perforation creates in the well, in the tubing, in the casings as well. These topics will be evaluated. So the thing is, in the first 2 weeks, the information that we will give will be very useful. They will be basic, of course, but they will be very useful for the topics of third and fourth week. So let me now share my screen with you and start the first week. Huh? All right. Now the screen can be seen. Can you please confirm it? You can see the screen?
Yes, it's visible.
All right, very good, very good. All right, let's start. Okay, so the objectives of this session will be the definition of the rock cycle, the 3 main types of rocks, which will be useful for reservoir engineering, especially the plate tectonics and its effects, the process of the sedimentation, formation, migration, and trapping of oil and gas, the basic rock structures and their importance. And in the second part, it will be related to reservoir engineering. It will include the rock properties. As you know, porosity, permeability terms, we will redefine this, the wettability term as well. The fluid flow and the dry mechanisms will be included. So in the end of this session, you will be able to identify all these parameters. Okay. So let's start. If we would like to talk about the geology, so we have to start with the size of the earth and the structures beneath the earth, right? So the earth divided into 3 different stages. We call it from the ground through to the deep side, up to 3,000 kilometers. We can call it mantle. And from 2,900 kilometers to 5,100 kilometers, we call it outer core. And from 5,100 kilometers to 6,378 kilometers, we call it inner core. So, when we are talking this, we have to scale it in our mind like when we go to around 6,000 kilometers, we are reaching the core directly, right? So it will be included in one part of our mind. So it's already known by the Greeks for thousands of years actually. Okay, but it's not turned until the 20th century. It could not be proved until the 20th century about these three layers. But in the 20th century, it's proved and these sections identified. Okay. So the rock cycle. The rock cycle first actually proposed by James Hutton. It was almost 200 years ago. The rocks at the surface are weathered to form the sediments, which is then buried. These sediments are cemented and compacted to form sedimentary rocks. Tectonic processes may then cause uplift, which may eventually cause these rocks to be exposed at the surface. Actually, where they are weathered and start forming sediments again. If the burial is deep enough, the rock undergo metamorphism due to heat and pressure. Again, tectonic processes may cause uplift, as can be seen in the picture, may cause uplift, exposure weathering, and sedimentation as well. If burial continues even further, the rocks may be melted and reabsorbed into the mantle. Actually, James Hutton mentioned that he mentioned that this will be done in a continuous section, and loop will consist as a loop. So what's going on? Weathering and erosion happens, deposition in oceans and the continents, form sediments buried, and liquefaction happens, and sedimentary rock forms. The exposure of the heat and pressure, these sedimentary rocks turn to metamorphic rocks, and then it melts and involves to magma. Then the magma shows a cooling when it comes to upper parts of the crust, upper parts of the earth. Then it forms igneous rocks. Then again, uplift happens and weathering and erosion, and as a loop, it continues as a cycle, and forms this type, the rocks, the rock types formed like this. So the classification of these rocks, let's go a little bit more deeper. So three different classification can be given in here: igneous rocks, sedimentary rocks, and metamorphic ones. So the source of material, the igneous rocks, the material is molten materials in deep crust and the upper mantle. For the sedimentary ones, weathering and erosion of rocks exposed at the surface, as mentioned in this cycle. For the metamorphic rocks, rocks under high temperatures and pressures in deep crust forms this type of rocks. Rock forming process, when we check the rock forming process, the igneous rocks formed by crystallization. It's actually the solidification of melt. The sedimentary rocks, sedimentation, as mentioned, sedimentation and burial, and also liquefaction, the reason of forming of these rocks. The metamorphic rocks, recrystallization due to heat, pressure, or chemically active fluids. So the three major rock types formed like this. So let me give some examples to igneous rocks, starting with igneous rocks. So here you can see four main types of the igneous rocks. The first one is basalt. The basalt actually formed at the mid-ocean ridge volcanoes, typically very dark in color, and with very small crystals in it. It includes. The second one, you can see gabbro. Gabbro formed deep in the crust from mantle material, typically coarse-grained and dark in color. Then another one is rhyolite. Rhyolite is a fine-grained extrusive rock actually. It is rich in silica material, and it causes the pale color. The color is pale. The granite, the fourth one is granite. It's also an intrusive rock, so coarse-grained rock. It is also rich in silica. It has to be light in color mostly. So these are the main igneous rock types actually. The metamorphic ones. The first one I can tell you, it is gneiss. Gneiss is typically metamorphosed igneous rocks actually. The banding comes from the minerals and the parent rock that have heated and melted and separated out in the orientation of maximum pressure. Another one is mica schist. It's characterized by a parallel arrangement of the body of constituent minerals. They are generally coarse-grained, and the mica refers to the dominant mineral in the rock, actually. Another one, slate. Slate is typically dark in color, formed from shales, of course, highly foliated and cleaved easily. Another one, marble. Marble is known very well, actually. It's also metamorphosed limestone. Usually almost pure. It formed as pure calcium carbonate, which also we are seeing this in geothermal wells a lot as well. And another one, quartzite. Quartzite is a metamorphosed sandstone. It usually actually forms from pure silica dioxide. Pure silica dioxide. All right. So let's talk about the sedimentary rocks a little bit. Sedimentary rocks are formed from the material of other rocks, which could be igneous, metamorphic, or other sedimentary rocks. This classification splits those rocks which form from materials transported from one place to another. Clastic rocks from rocks which are created from materials in their space of formation. There is no transportation. Non-clastic rocks. The third category, actually, we call as sedimentary rocks. It's very important one for actually oil industry, for reservoir engineers, because most of the source rocks and cap rocks are formed from these parts in all hydrocarbon reservoirs, actually. So when we classify these, we classify as clastic and non-clastic, as I mentioned before. Clastic rocks are sandstones, shales, and silts. Consist primarily silicate minerals, silicon dioxide, the first one. Classified based on mineral composition and grain size. Formed from the materials of older rocks by the actions of erosion, transportation, and deposition. For the non-clastic rocks, these are carbonates and evaporites. Carbonates are formed as biological, and evaporites formed as chemical by using chemical reactions. Primary non-clastic rocks are limestone and dolomite, formed by chemical or biological processes, and then deposition happens. For the clastic rocks, classic rocks are mainly sands, silts, and shales. The difference is, of course, the size of the grain, mainly. Sands, as you know, sands are reservoir rocks. It can be shale, it can be source rock and cap rock. These shales are very fine-grained and also contain fluids, can only leak out in the geological time very slowly, actually. These can be classified as clastic rocks. Let's see some clastic rocks. The first one, I can see breccia. This is assorted fragments, actually. This doesn't have any transportation, stays in the location, and often formed from limestone, collapsed structures, or within a fault plane. If there's a fault in the close parts of a fault, you can see this mineral, this rock a lot. The another one is conglomerate. It's a mixture of pebbles and fragments ranging widely in size, actually. Pebbles are often well rounded. I don't know, it can be seen clearly from the picture. It implies some transportation is available. It can migrate, but in a very high energy system, it's possible. Oftenly, you can see these type of rocks in the beaches, near of beaches. It can clearly seen. Another one, the sandstone. We are very familiar with this actually. It's well sorted, almost pure quartz grains. Can be formed in deserts or in shallow marine conditions. It's very widely. You can see in most of the parts of the Earth's surface. Right. Another one, shale. It's dark, heavy, fine, very fine-grained material rock. It formed in deep sea environment. It has a very low porosity, as you know. In that, if you are familiar with unconventionals, it has very low porosity and permeability. It actually it can be used in the nature. It can be used as a caprock, actually, very fine, excellent caprock. So, okay, let's talk a little bit about the grain size. For the shales, the grain size is lower than 0.004 millimeter. If the grain size is between 0.004 and 0.06, we call it siltstone. If it is between 0.06 to 0.2, we call it sandstone. If it is between 2 millimeter to 256 millimeter, these are mostly conglomerate and breccia. They all originated from the silicated minerals, silicon dioxide, right? So for the non-clastic rocks, yeah, means carbonates and evaporites. For the non-clastic rocks, sorry. For the non-clastic rocks, we can say that for the limestone, mainly formed by calcium carbonate, and usually these are reservoir rocks. For the dolomites, these are also reservoir rocks and formed by the replacement of some calcium by lesser volume of magnesium in limestone. It has more porosity compared with the limestone. And the third one is evaporites. Salts and anhydrite crystallize from evaporating seawater in enclosed basins under dry climatic conditions. So these can also forms like shales. These can also form a good caprocks. A good caprocks when you are making making an interpretation in logging, for example. The first thing that you will do is to check the shale and evaporite structures, right? So another non-clastic sedimentary. This is an example which has been taken from the Sahara Desert. It's 10 centimeters long. This is gypsum, and you can see why they are saying desert rose to this from the structure. This structure is formed by the combination of the anhydrite with water, definitely, and it's called gypsum. Another one, halite. It's actually the main material of this is, as we told, salt. This is a sample from Strasbourg, Germany. It formed as crystals like this. Let's talk about carbonates. This is a carbonate rock example from Oman. You can see the structure clearly and the fossil structures as well inside. So, when we talk about the sedimentary rock abundance in the world, the limestone and dolomite means non-clastic reservoirs consist 14% of all, and siltstone and shale includes 75%. for all structures we are talking, of course, the abundance of major sedimentary rock types. Siltstone and shales, nearly 75%. Sandstone and conglomerate is nearly 11% we can classify for this clastic rocks. All right, not reservoir rocks, clastic rocks, sorry. Another thing is the plate tectonics and the plate tectonics theory. Actually, the plate tectonics theory, it's a theory that underpins most of the modern geology. The basic theory is that the surface of Earth is made of several segments. They call it plates. These plates move around the globe while being created and destroyed. It explains many things actually, what happens around us when we are observing. Such as, for example, rock types that indicate desert climates in North England. Rather than have to move the climatic belts, it's in the continent itself that has moved. All right. So this plate tectonic theory actually explains most of the questions that we face regarding on the geology in the Earth. All right, there are plates. These plates are movable. They are moving and going beneath of other ones and going upper part of other ones. They, with millions of years, they are forming the mountains. They are forming the deeper parts, the deserts. Everything is a result of these movable plates. And this theory is the most acceptable one actually currently, and gives the details regarding on it forms this modern geology and gives the details regarding on how it has to be happen and how it happened previously. So what are the evidences of this plate tectonics theory? The plate tectonics theory, first of all, says that the Earth has one continent in the beginning, only one continent. And then these continents are separated from each other and then form today's continents. So we can see from the picture clearly actually. As you can see, there are some belts which are matching clearly from one continent to another. For example, the fossil remains of Cyanogratus, as you can see, from South America. When you combine the continents, when you combine the both continents, you can see it's continuous as a belt. It can see, for example, the fossils of Glossopteris. It forms a belt from Africa through to India and through to Antarctica as well. And sorry, this is green one actually, Glossopteris. And another Triassic land reptile, Listosaurus. You can see Africa, India, and Antarctica. So these fossil records shows that if in the beginning there was one continent, definitely. Another proof of this is of course the Mid-Atlantic Ridge. It's still opening and it's separating. It continues to separate the lands, the continents. So, as we said, crust is divided in rigid plates. These plates move few centimeters per year. Each plate moves few centimeters per year, and some of them, as I told you, for example, let's talk a little bit close to our location. You can see there's an Arabian plate in here. The Arabian plate has a contact with the Asian plate, right? And the Anatolian plate, as you can see in this part. So here it goes beneath the Asian plate, and the structure has some people from Turkey asking me why there's no oil in Turkey. So this is one of the reasons that we can explain. So Arabian plate is go beneath the Asian plate, and when in Arabian plate you can produce in 2,000-3,000 meters 4,000 meters. When it comes to Anatolian part, it go beneath the Asian plate, and the Arabian plate will be found in 9,000, 10,000, 12,000 meters. So because of that, it will be very hard to find an oil belong to Arabian plate in Anatolia. And another reason, of course, the earthquakes, and the earthquakes is the main reason. Anyway, so you can see that why geology is very important, very crucial to describe the places that we can find oil. So we told that place move a few centimeters per year. The driving force is convection currents in the mantle. Convection currents in the mantle. All right. So what are these convection currents? Okay. So we can say that plate tectonics accounts for nearly all geological processes in the Earth crust. Plate movements are caused by convection cells in the upper mantle. We call it asthenosphere. The figure shows magma rising to form new crustal rocks at the mid-ocean ridge, which is spreading laterally. As new crust or lithosphere is transported laterally from the mid-ocean ridge, it cools and its density increases, causing a crustal sag relative to the ridge. Where dense oceanic crust collides with continental crust, the oceanic crust is thrust under the continental lithosphere in a process called subduction. Subduction. As subducted plates are carried down, temperature increases, and eventually the lid of the plate melts. So strong earthquakes, as I mentioned before, strong earthquakes and volcanoes are common in these subduction zones. So we talk about the conversion. So let's talk about the diversion. What is diversion? Diversion means spreading. These boundaries formed in new crustal rocks. Okay, we call it lithosphere, formed in the lithosphere part. And actually volcanism and earthquakes are common at these plate boundaries. The example of actually the example I talked mid-Atlantic ridge. The example of spreading place is the northern mid-Atlantic ridge actually. This is what I can say. Actually, many geologic processes occur along the convergent boundary, not divergent, convergent boundary, with the creation and upwelling of magma, volcanism, mountain building, creation of deep sea trenches, and earthquakes as well. All right. So, types of plate boundaries. Types of plate boundaries. These plate boundaries, three main types of plate boundaries we can talk in here: divergent, convergent, and the transform boundary. You can see the directions clearly here, the transform boundary as well. So, at plate boundaries, there are several possibilities, such as manufacturing of a new oceanic plate, plates slide along each other, as you can see. Continental plates crash into each other. Oceanic plate is subducted under a continental plate. And types of crustal plate boundaries are defined on the basis of relative movement. It changes in any part of the world, but mainly consists of maybe you can see the combination of these three as well in some places. But mainly we can classify in three different groups. So we talk about the sedimentation, burial and nitrification, and how sediment rocks formed. Let's continue a little bit more about sedimentation. Sedimentation actually happens as in horizontal waves. Okay, this will be useful when we are talking in the fourth week when we are talking about the perforation. Sedimentation is in horizontal layers, happens in horizontal layers, buried and litificate as horizontal layers. So there is a principle, we call it superposition, principle of superposition. It says the oldest rocks always on bottom and the youngest on the surface, right? So never forget these, oldest in the bottom and the youngest on the surface. So we will talk this later on when we are in the perforation topic. Okay, so sedimentation and diagenesis. The sediments settle in relatively low areas. For example, lakes, riverbeds, or below sea level. Sorry. They remain there if space is created for additional layers on top. As the sediments accumulate and get buried, the temperature and pressure increase, expelling water from the sediments. We call it diagenesis. Clay becomes shale, losing over 80% of water. As you know, clay has most part of the clay is water, H2O. And lose nearly 80% of these water in the process, and consist shales. And then sand becomes sandstone, losing only 5 to 25% of its water. So losing water, it means that losing water can form another type of rock, right? Another type of rock, we can say. So sedimentary environment, what we can say about sedimentary environments, different sedimentary environments result in different rock characteristics. Some rock characteristics allows rock to become reservoir rocks as they are both porous and permeable. It also, we will talk about this, it also affects the wettability behavior of the rock. So the reservoir rock likes water or doesn't like water, likes oil. So in of course in a micro scale we are talking about. So the tendency of the rock change your recovery definitely. All right, we will talk about this later. So various sedimentary environments. Actually, this is an attempt to give some idea of the various sedimentary environments. This is somewhat foreshortened version of this. The continental, it can be clearly seen here. I don't know. Okay, in the continental part, we say that the alluvial environment encompasses the river channels itself, the border of the channel, and the flat valley floor on either side of the channel that is covered by water when the river flows. Okay, a desert environment is arid. You can see here. A desert environment is arid. Sediments that is formed by a combination of wind action, the work of rivers that flow mostly intermittently, of course, flow through it. And the shoreline part we are talking about, shoreline environments are dominated by the dynamics of waves, tides, and currents on rocky and sandy shores. All right, mostly. When we talk about the marine environment, of course, we say that continental shelf environments are located in the shallow waters of continental shores, where sedimentation is controlled by relatively gentle currents. All right. So continental margin environments are found in the deeper waters at the edge of continents, where sediments are deposited by a special type of deep water current. Okay. All right. Let me pass to depositional environments in this case. As we mentioned, the reservoir rock types are clastic or non-clastic, can be classified. The positional characteristics of rocks affect reservoir properties such as pore volume and flow properties. The type of porosity especially in carbonates, is determined by the depositional environment. The depositional environment determines the geometry of a reservoir. Rivers, deltas, reefs actually have specific external geometries and internal properties. So, the source rock, hydrocarbon formation source rock, we will talk about a little bit. As a subtopic, we will talk about the creation and the accumulation of hydrocarbons, of course. So, how it happens, how a hydrocarbon forms, and how it preserved. So, we will try to describe a little bit about this. So, first of all, the formation of a hydrocarbon needs a temperature window. If the temperature is too low, the organic material, it's not possible that the organic material transform into hydrocarbon. If the temperature is too high, the organic material and hydrocarbons cannot be formed because they all destroyed. So the temperature window, when we checked all the cases around the world, the temperature window is between 140 Fahrenheit to 325 Fahrenheit. Starting from 140 Fahrenheit, when we go, when the temperature increased, oil start to form, and then if the temperature exceeds a level, it start to gas to be formed. All right. So when you exceed when you are below the 140, so temperature is not enough to form hydrocarbon. If it exceeds the 325, so it's very, very high, and it all burns and destroys. Okay, so for the hydrocarbon accumulation, it's crucial to enable 5 different factors, mainly we can say. So I am talking about the conventional one, of course. So these are major source rock, migration pathway, reservoir rock, trap, and sieve. Okay, these five parameters has to be involved in a structure to make it enable to form a hydrocarbon. So you can see in the picture clearly. So the accumulation of the organic matter happens in the source rock. We can see in the red. And the preservation of this organic matter, and it exposed to thermal maturity with the subsurface heat, which is inside the oil, inside the temperature window, of course. We call it oil window. So this source rock, from this source rock, the fluid migrates through to the upper parts until it finds a cap rock, and it forms. It stays when it finds a cap rock, a kind of anticline structure, right? So we can say that the source rocks, in terms of source rocks, 65% of source rocks in the world is consists of shale structures. 12% marls, 21% carbonates, and 2%, less than 2% actually, coals forms source rocks. The hydrocarbon migration, it actually happens in 2 different stages. The first one is the primary migration, we call. It happens from the source rock to a porous rock. This is a complex process and not fully understood actually currently. It's probably limited to few hundred meters. And the secondary migration is along the porous rock through to the trap. As I mentioned, when it finds a trap, it stays. But until it finds a trap, it continues to migrate. So this occurs by buoyancy, capillary pressure, and hydrodynamics through a continuous water-filled pore system. It can take place over large distances, of course. So let's talk a little bit about the hydrocarbon traps. Hydrocarbon traps mainly faults and faults that form effective structures to trap hydrocarbons. Oil and gas accumulate in the dome, and the seal prevents them from escaping upwards. If in a location, if there is a too much earthquake and the movement is too much, it's impossible to have capracks because of the forming of faults, cracks, other things, and it moves through to the surface. I couldn't check. All right. Okay, so we said that what we said, a seal must be impermeable. This is the first thing. A seal must be impermeable. If the location is too much movable in terms of earthquakes and other things, so it forms false cracks, and the impermeability is going out, and we cannot talk about the impermeable structure. So it loses the specification of being a capra. The impermeable rock. So the types of seals in the world, again, 65% consist of shales, 33% evaporites based on salts, and less than 2% are carbonates. So in the evaporites are very useful for this. Actually, what's going on with the developing technologies, currently, there are some projects worldwide which are trying to use evaporize as capracks. There is no oil and gas beneath that, but there are some evaporize which are very suitable to be a caprack. And what's going on? You are injecting your natural gas, for example, beneath of these and using it as a storage places. So there are some projects currently. I think Turkey has one of them as well in the Salt Lake. So as we said, mature source track and migration path definitely required. Okay, the trap. A geometric configuration of structures or strata in which permeable rock types, I mean reservoir rock types, are surrounded and confined by impermeable rock types. These are structural traps, stratigraphic traps, and combination traps. So in the structural traps, these are very common ones, as I told, anticlines are the most common one. Faults and salt diapirs, salt domes. Okay. In the stratigraphic traps, again, salt domes can be classified as stratigraphic. I will talk about this. The unconformities, reefs, and other types. And the combination traps, we say we can see more than two of these as a combination. For example, you can have fault and you can have reef as well. You can your structure can show unconformities in an anticline structure. So you can see a combination of all of these as well. So let's talk a little bit about the salt diapirs, dome structures. Oil and gas migrate upward from the source bed until trapped by impermeable caprack, we say. So one of these are salt structures. So you can see, as you can see in here, in the upper part, there is a section which is very conventional, right? But in the lower part, there is a salt dome. And this salt dome, when oil and water migrates, it comes to this salt dome and stays in there. So trapped by the salt dome consists a kind of trap for oil. Okay, you can see. Yeah, faults. Faults are one of the main reasons, of course. Like caprock, in the upper part there is a impermeable zone, and because of the faulting, the impermeable zone comes to the lower part, and gas oil traps in this part, right? So this is another one. Also, unconformity trap. It can be, the layers can be formed in a unconformity like this. We said it has to be horizontal, right? But here there is no horizontal section, so it can be formed in this section as well. It's unconformity trap. Okay, the structures. The type of structure depends on the stress regime and the rock type, of course. There is a brittle and plastic deformations we can say, sorry. Brittle deformation yields faults and fractures, and plastic deformation yields faults and disappears. At this point, the stress regime governs the shape of the structures. Let me, yeah. So here you can see the faulting, which shows, which combines, which consists a barrier for the paths. This is the first one from the Canap Canyon, Utah. The second one is from Anatolia. You can see the faulting in here clearly. So if there's an oil, for example, if there's an oil layer in here, so the impermeable zone, it will close as a trap. It will form a trap, and the oil will remain in here, right? Okay. So the plastic deformation, you can see we said brittle and plastic deformations, right? So if there's a brittle deformation, so faults can be formed, right? It's broken. So if there is a strength and the force exceed the strength of the rock, so it broken and formed faults. So this is a very good example for brittle deformation. When we come to plastic deformation, you can see two examples in here. So the force applied is not exceeding. The force applied is not exceeding the strength of the rock, and it shows a tendency to form like this. Okay, folding. Okay, two different examples can be seen here, and this folding resulted in having an anticline and synchronized structures, right? And we said the youngest, don't forget, we said the youngest rock will be in the upper, oldest will be in the lower part, right? Okay. So, yeah, let's see all the type of traps in one figure in here. So anticlinal structures, we said, these are the most common ones. 75% of all reserves formed like this. The second one, faults, we mentioned. It's nearly 1% of all reserves like this as faults, you can see. 2% as salt disappears can be seen. Unconformity traps, 3% of all. Reef structure can be seen as 3%. Okay. Other stratigraphic 7%, and the combination of all these is about 9%. Can be seen in all reservoirs of the world. Current reservoirs, proved reservoirs. So the seal. The seal is impermeable barriers, capracks, and the type of seals, again, 75% consist of shales, 33% evaporize, and 2% carbonates. Okay. So, for the reservoir structures, there are many type of structures actually, many other types of structures, and the criteria for a structure, it has to be formed as a closure. The fluids are unable to escape and be large enough to be economical. For example, in Anatolia, we have some reservoirs which are not useful actually. Yeah? They are opening the reserve. They are opening it with up to pressure 2,000, 3,000 psi. It's producing 12 days, 15 days, and then it's go to depletion. So these are not useful. It has to be large enough to be economical. Okay. So the exact form of the reservoir depends on the depositional environment and post-depositional events such as folding and faulting. So here there is a figure, as you can see. There is a fault in here. There are 3 different units and 4 different wells. Some wells, one of the wells are very close to the fault, as you can see. And the length of these wells are different. Probably the third one is producing from the lower parts as well. So multi-layer one. And the second one exceeded these 3 layers. The fourth one also exceeded these 3 layers. And the first one, you can see it's producing directly from the unit 2. All right. So here we can say that these 4 different structure, with these 4 different wells, productivity changes differently actually. So please think about this and try to understand the mechanism. Which one produce better and the productivity index has higher? Think about that, and next week we can talk about this. I will explain in the first slide of next week. All right. So let's continue. Let's have a talk about the reservoir. Reservoir actually requires 2 basic parameters. One of them, porosity, we all know. The other one is permeability. So most common reservoir rocks are sandstones, 60% sandstones and 39% carbonates, and 1% the others, of course. So now we will talk about these parameters. So up to now, we defined the rock cycle, rock types, plate tectonics, sedimentary rock formation, migration, and trapping of hydrocarbons, and the rock structures involved in hydrocarbon trapping. So let's pass to another part related to reservoir. First of all, I will talk about porosity and permeability, and then explain fluid flow through rocks, saturation, we will talk, wettability, and oil properties a little bit. Explain in details the 3 reservoir drying mechanisms, enhance oil recovery a little bit, and secondary recovery, and then we will finalize this section. So let me continue. Yeah, the porosity, all of us are familiar with this, of course. The representation range from 5 to 30% generally. The primary porosity formed during the deposition and the secondary formed after deposition, right? So you are seeing an example of rhombohedrali packed spheres in here. If your rock grains formed like this, your porosity will be 26% nearly. But it's not being like this, of course, in the nature. It's mostly being like this: grain sorting, sealed clay, and cementation of materials included in most of the reservoir rocks in the nature, right? So we will see all of these. The porosity rock matrix and pore spaces. We say that the open space within the rock is the pore space, is called porosity, and it's always measured in %, right? Okay. So if there is a cubic packing, the porosity value is 48% mathematically, right? It's rhombic packing like this. The porosity 27%. If there is two spheres, okay, two type of spheres, then the porosity decreased to 14%. Okay. Okay. So the three main types of porosity. First of all, interconnected porosity. This is multiple pores passage between grains. The fractured porosity, only one pore passage, like cracks. Okay, can be a good example for this. The isolated porosity, no convection, no connection between the pores. So if we combine 1 and 2, interconnected and fractured, it gives us the effective porosity. Okay. Ratio of the effective porosity to total porosity is very important. It gives an idea regarding on the permeability too. The porosity is not affected by grain size. The porosity is affected by grain sorting and angularity. Okay. So the interconnected porosity, as you can see, the blank place, empty places between the grains are connected to each other. And if the structure like this, so you will see 15 to 30% porosity. Okay. The fracture porosity, if there are fractures, cracks, okay, wax. So these reach 1 to 3% and maximum 12%. If there's isolated porosity, you cannot measure this, of course, from your logs, and it will have lots of trapped materials. So the primary porosity, we can classify in two types, like intergranular. We are seeing this in sandstones like this, fine grains, and intragranular. This is the example. Limestone is a good example for this. So it's very complex structure, and the porosity not like we are getting it from sandstone, of course. So other types we can say for the shrinkage, fenestral and intercrystalline, if there's a crystal structure, so you can see porosity like this, structure like this, of course. And the solution, leaching of solution, we can say there are moldic structures and vaggy structures as well. You can see the structure in this as the second figure. All right. And if there are fractures, you can see the figure in the, you can see the structure as in the third figure. Okay, so how we are getting this porosity? What are the porosity tests? Okay, so two main types of gathering this information. One of them is logs, of course, gives you the total porosity values. Sonic logs, neutron logs, and density logs can be used for this. And the second one is the core tests. Core tests gives you the effective porosity values. Water saturation, gas saturation, and mercury injection experiments gives you an idea regarding on the porosity. These two methods, of course, the core tests logs are more suitable to apply. When we come to core tests, there are not too much companies are performing this one. To take in situ core samples actually is can be a little bit tough. You have to take your samples in your download samples in situ, and you have to preserve it up to surface and preserve until it comes to the laboratory. So most of the companies are taking it as from the logs actually. So the permeability, while porosity is the measure of fluid contained with the rock, the pore spaces must be interconnected for the fluid flow. So is there any question here? Okay, no, registration form is asking. Okay. So I'm continuing. While porosity is the measure of the fluid contained with the rock, the pore spaces must be interconnected for the fluid flow, right? Fluid flow. Matrix permeability in oil reservoirs varies between 100 millidarcy to 3 darcy. Fracture permeability 5 darcy to 15 darcy. So if you have a structure, with fractures, okay, so your permeability will be much more higher compared with the unfractured parts, right? In here you have to make an optimization, of course, if you are producing in a fractured zone. So you have to optimize your fluid flow. It's good to produce more, of course, but you have to optimize if there is a water, for example, coming from the lower parts. So there can be being a conic water conic issue. So it will create some problems. So you have to optimize your rates. You have to optimize your flow. It will be crucial actually. So Henry Darcy, as you already know, but I will continue, I will repeat it in here as well. Henry Darcy investigated the flow of fluids through porous media in 1856 and devised a measure that carries his name and is represented by a small constant. So, okay. So here you have an inlet surface, an outlet surface, and you have a location which has L length, right? So it defines these terms are defines the permeability. What is the permeability? It can be said that fluid allows 1 centipoise viscosity to flow at a velocity of 1 centimeter per second for a pressure drop of 1 atmosphere per centimeter. So Darcy gives this one. It's the parameters related to the area, the pressure difference, the rate, viscosity, and the length of your control volume. Okay, so effect of grain permeability. So if your grains are large, you will have higher permeability. If your grains are small, so it is a direct proportion. If your grains are small, it will show a lower permeability because the parts which can be considered in the micro scale will be upper, and the capillary effects will be dominated more compared with the large grains. Okay, so for the you are seeing here the capillary pressure with water saturation, capillary pressure change with water saturation. So when you have 100% oil production, you can see in the upper part, in the oil zone, all right? So oil-water contact. Oil-water contact is a transition zone when you have a lower permeability, reservoir permeability, your transition zone will be longer. All right, the movement will be slower, and your transition zone will be longer. For the permeability tests, you can gather these transition zone levels and free water levels and oil levels. These zones can be gathered by using the permeability tests. These are MDT, RFT, well testing, and core sampling as well. Core sampling is also enables this if you are getting the course as preserved. This is very important. So another thing is in terms of wettability, your core samples show, for example, if you are in the oil zone, your samples will show more oil wet properties. In the water zone, more water wetting properties they will show your eyes. So the ability, as we said, the ability to flow through the rock is the function of saturation, wettability, and oil properties. So let's talk about the saturation. Saturation is the amount of water per unit volume. And the amount of hydrocarbon, of course, amount of hydrocarbon per unit volume, we can say. Okay. Water saturation and oil saturation. We will refer oil saturation as SO, water saturation SW, of course. So, the percentage of pore volume occupied by particular fluid, actually, another term of saturation. So it can be oil, gas, and water. All right, in the rock sample. If it has a small grain size, you will get higher irreducible water saturation. If you have large grain size, you have lower irreducible water saturation. Why? Because of the effect of capillary forces. Because we are talking about the microscale in here, so the effect of capillary forces will, if you have smaller grain sizes, effect of capillary forces will prevent your fluid to flow. Okay, so irreducible water saturation will be high. So let me talk a little bit about the wettability. Actually, wettability is can be described as the tendency of a fluid to spread on a rock surface while this fluid and also the rock surface is in contact with another immiscible fluid. In other words, it's the choice of rock, the tendency of rock to like one of the fluids compared with the other. Okay. So if it is you can see in the first picture, the rock is filled with oil and water here, you can see. In the second one, the water wet condition. What's happening? Rock likes oil. Say rock likes water. Okay, water wet condition. Rock likes water, and rock has a tendency to take the water to take the water on its surface. So because of that, you can see the water comes to the surface of the rock volume, rock grains, and the other parts shows oil. Okay. Okay. That's.
So sorry, we have a question, please. Can you explain?
Yes, please.
A student asked that, can you explain more in detail the effective permeability, horizontal and vertical permeabilities, and when we will use just the total permeability or others, effective, horizontal, vertical?
Okay, so the horizontal and vertical permeability, of course, very good question, very basic question, but it's a good question. So when we are talking about the vertical well or horizontal well, the definition of these terms are very crucial. I saw a lot of cases which uses the horizontal permeability for a horizontal well. Okay, so it gives a lot of it results with a lot of problems. So the horizontal permeability, the vertical permeability actually, the vertical permeability is used when actually it has a directions. Okay, it has a directions, vertical direction and horizontal directions. If your vertical permeability in horizontal, you are talking about the horizontal direction, so you will take horizontal permeability. If you are talking about the vertical direction, you will take vertical permeability in here. The ratio is 1:10. All right, 1:10. Your vertical permeability and horizontal permeability will be the ratio will be 1:10. So I will mention about this in next slides as well. We will continue with this one. Okay, let me continue with the wettability issue. I will turn back to the permeability issue. Okay, so we were talking about the contact
We have,
angle.
so sorry, we have another question and it's finished. A student asked that free water level and oil water contact is same things. What's the difference?
Wait. Okay. Free water level and oil water contact are not the same things. Free water level includes 100% water. If you are beneath the free water level, if you are on the free water level and beneath your free water level, it means that you have 100% water in your pores. The upper part, it starts to have some oil in your pores, okay, and the amount of the oil when it increase, the amount of oil will increase as well. And if you have oil water which are contact in your rock sample, if you have both oil and water, it means that you are in transition zone. All right. So this part is the transition zone, and when you reach the lowest oil, so oil phase will be finished, and then in the lower part of this, you will see directly water, only water, of course. This is dynamic as well. This is dynamic. For example, you can see for example, let's say this is 3,000 meter. Your oil water contact. 15 days later, you produce a lot. When you measure it, your oil water level can come to upper parts, of course, 2,800 meters, 2,900 meters. Okay, so this is totally dynamic. So that's why I am saying that the optimization of your production is very crucial to prevent conning issue. In multi-phase metering issue, because one of the main duties of multi-phase meters are preventing this conning issue. You are continuously measuring your production and the water levels of your production daily with multi-phase metering. And if there's a conic problem, water conic problem, so you have to lower your production in that wells of a field, and you have to increase your production in places that there are no water or lower waters. So you have to make a reservoir monitoring and the measurement of your reservoir to prevent any water conning, of course. So this is totally a dynamic issue, but your free water level directly means you have 100% water. Okay, above your free water level, you start to get oil. You have oil, but in your free water level and lower of that, 100% water. Hope that it clarified. Okay, so yeah, we were talking about the contact angle as a measure of wetting. This is another crucial issue actually, which mixed a lot. So if there's a complete wetting, means that you have zero contact angle. Okay, so your liquid totally spread on the surface of your rock sample. For example, I had a chance to work with these a couple of years in the laboratory. For example, it's actually a little bit hard for a rock sample to see water spread on the surface with zero angle. It's very hard. 10, 20 degrees you can see, but zero is very hard. But there are some chemicals which are spreading, fully spreading, such as dodecan. Dodecan is spreading with zero contact angle. So you can use it as a reference fluid actually. In the second one is partial wetting. The contact angle is around 30 degree. So you can see a structure like this. These measurements also can be done by using a galvanometric measurements. You can use it with core sampling by using cores as well, amount USPM indexes you can use, and also you can use an observation with a galvanometric measurements. You can see the droplet like this with 30 degree. If the gas is octane and liquid is water, uh, low degree of wetting if the contact angle, for example, here is the contact angle 153. These are real measurement results, by the way. So if the gas phase is isoquinone and the liquid is water, you can see something like this. So herein, it happened with the gas and liquid phases. But in the reservoir, we have gas, of course, but we have water and oil, right? Water and oil phases as well. So we can use this for water and oil and describe our rock sample is oil wet or water wet. Okay, the implications of wettability. Wettability affects the shape of relative permeability curves. Oil moves easier in water wet rocks compared with oil wet rocks because your rock doesn't like oil and want to get rid of it, right? Simply. So primary oil recovery is affected by the wettability of the system. A water wet system will exhibit greater primary oil recovery, and oil recovery under water flooding is affected by the wettability of the system. A water wet system will exhibit greater oil recovery under water flooding. So here in the volumes comparison from the downhole and the surface. For example, your oil, when it comes to surface, of course, what it will be, it will expand the gas phase. Your pressure is decreasing, temperature is decreasing. When it decreases, you will have a solution gas, right? So this solution gas will be included, especially in multi-phase flow metering calculations. These are very crucial. So your RS solution GOR will be included to the gas phase, right? So your gas phase, your free gas will be included as well. Your solution gas from oil will come, and in the water also, what it will be, there will be a gas phase. When it comes to the surface, there will be a gas phase of the water as well. So it will be a solution gas too. It will be included. So in your gas phase, when it comes to surface, you have to include your free gas. Your solution gas comes from the oil phase. Your solution gas comes from the water phase always. Reservoir dry mechanisms. The hydrocarbons will flow if the reservoir pressure is sufficient to drive the fluids to the surface. Of course, if not, they will need some artificial lift operations to take it to the surface, right? As the fluid is produced, reservoir pressure drops according to the reservoir drive mechanism. The reservoir drive mechanism depends on the rate at which fluid expands or replaces the produced fluid. So what it means? There are three main reservoir drive mechanisms. These are solution gas drive, we call it depletion drive, gas cap expansion drive, and water drive. Water drive, and in another words, we talked about coning, right? What's going on? Why it's being coning? It's the water phase with the production. The water phase has a tendency to come the upper parts and make a conic issue. It replaces the place of oil and gas. And your water oil contact level will change, right? Okay, so the solution gas drive means depletion drive. Herein, oil is produced by the expansion of the reservoir fluids and the gas dissolved in the liquid phase. Gas dissolved in the liquid phase. So, in the initial conditions, what's going on? The reservoir pressure is above your bubble point pressure. No initial gas cap in here and no water influx. Okay. So by the time with the production, the gas phase inside your oil start this solution as a solution gas, it start to expand and it forms a gas phase with the production. Okay. So Herein, um, the typical behavior of the oil production can be seen as in the figure. An initial high oil production is followed by a rapid decline. Okay, and also GOR value, gas oil ratio value, has a rapid increase and then decline. Okay, so the gas oil ratio, as I told, to the high permeability to gas, okay, shows a peak. The reservoir pressure exhibits a fast decline as well. So for the gas cap expansion drive, in here you have a gas phase. In the initial condition, you have a gas phase, and this gas phase assists as pressure, assists your oil phase, okay, and you start your production. So below the bubble point, the expansion of fluids are mostly negligible, okay. The drive is achieved by the expansion of gas cap and the release of gas coming out of the solution. Herein, this is the case with no water influx, of course. So, the gas displacement. Gas is more mobile than oil, as you know, and less viscous. So, it takes the path of least resistance along the center of the larger channels. You can see two different figures in here. In the first one, sand grace and irreducible water part you can see. It's a little bit, actually, there's a water phase in here, okay? So your gas phase has a tendency to be like forming a channel between the oil phase, okay? Uh, in the second one, the gas phase, you can see the oil particles in here as well. The gas phase has a tendency to go along the pores and be the dominated phase, okay? Okay, so in the gas cap drive, the reservoir pressure and the oil production results can be seen like this. Reservoir pressure drop at the start of the production, and oil production declines, gas production increase. When you see it has a it has a reverse proportion. Your gas amount is increasing and your oil production is decreasing with the same amount. When you add these two, it will give you the one, right? Give you the full length of your plot. The water drive. This is herein there is an oil phase in the lower part, and it assists the reservoir pressure. Okay. So the oil being produced is replaced by water, as I mentioned, to keep the pressure constant if the replacement ratio is 1:1. Okay, if the replacement ratio is 1:1, your pressure or your reservoir pressure stay constant. But if not, according to that, it will decrease. Yes. Okay. So the water displacement in this type, the remaining thread of oil becomes smaller by time. It finally breaks into smaller pieces, as you can see in the second picture. But some drop of oil will continue to stay as irreducible in the reservoir, right? In the end. So this type of drive usually keeps the reservoir pressure constant. After the initial dry production, water may be produced. The amount of produced water increases as the volume of oil in reservoir decreases. The dissolved gas in the oil is released to form produced gas. The gas-oil ratio will be almost constant over time since reservoir pressure is higher than your bubble point pressure. Okay, for the water drive, you can see the reservoir pressure. Please.
Hi, Jalal. Thank you for your presentation. I want to ask a question. Is there any differences between water flooding and water injection?
Okay, water injection is a process that you are making from your injection well and inject your water through to your reservoir, right? So water
Okay.
displacement is the process which happens inside the reservoir. Your injection, you inject your water reaches to your reservoir, all right? As in your process, most commonly your process. In your reservoir, your water start to displace your oil. You have to, as before, the optimization is everything. You have to optimize your rates, injection rates, according to the properties of the reservoir to enable a swept efficiency. Okay, you have to sweep efficiently your oil and gas. Okay, so it causes water displacement in the reservoir. Water injection is a process which happens in your valve. Okay, you inject it, but the displacement term used for the process in the reservoir. All right?
Yeah, it's clear. Thank you.
You're welcome. Okay. So, okay, we were talking about the water drive. As you can see in the water drive, this is the different process, by the way. Water displacement, this is the water displacement process is totally different than this. This is water drive. Water drive is your water is naturally in there, already in there. Okay, you are not injecting anything. It's already in there. When you are producing it, it in the lower parts, it assists your pressure and comes to the upper part, your water, right? Naturally. Naturally, yeah, it happens. In other part, you are injecting your water. You have to arrange it operationally. You have to arrange it in a smooth way to sweep efficiently your oil and gas. Okay, totally different processes. In here,
So
in
in
that,
this case, we should have an aquifer.
you should have. Sorry again.
Aquifer.
This is an aquifer. Okay, this is a kind of aquifer you can think about that. Okay, this is
Yeah.
aquifer. Okay, you have to have an aquifer, definitely, which assists your pressure, and this displacement will be like an occupation of your when you produce your oil and gas to the upper part, your water will occupy these pores. Okay, but it's not when you compare with the water displacement is much more controllable when you compare with this one. This one, you will have it's very hard to have a control of this. So because of that, you have to monitor continuously. So you have to prevent your coning issue, because when your coning, your water forms as a coning, okay, comes to your well, you start to produce your water directly. If once you start to produce your water levels will increase in the surface, and it will be, you have to shut in the valve to make it back again, to prevent your coning. For example, you have to shut in for 15 days, 20 days, whatever. This is the thing that you never want. You never want. Because of that, you have to decrease your pressure, decrease your rates according to that, arrange your rates instead of shutting the valve, and lower your conic, you overload water production. In a field, we are thinking about that, right? You have to produce more in the places, in the locations of the field which are less water. You will increase the production and balance your water to stay as stabilized. It's actually what we want, as we talk in this water oil contact figure before. Water oil contact figure, we want it to be stabilized. We don't want it to be to show sudden differences. Okay. All right. So herein, after the initial dry production, water may be produced, as we told. When we check the reservoir pressure in the beginning a little bit slowly decrease and now remains constant, because what happens, your water assists your reservoir pressure, and by time coning happens, and your water production increases. This is something that we don't want. Okay, so you have to decrease your rate, and your water levels will we remain like this in the same levels, right? Okay. So in the water drive, so it says, as you can see in here, it says abandonment. So we don't want it, we never want it to come to abandonment stage, right? So when we check this one in the water drive, the rate of oil increases. The water, if you the rate of your oil increases when your water phase production increases, the rate of oil start to decrease. Okay, and your pressure, as we said, remains constant after a while, and your GR ratio will be decreased. We have to be careful about this one. If your water level comes too high and your GR level comes to a certain level lower than the boundary, expected boundary, so it can be abandoned. You have to close your well, because otherwise you will start to produce directly water. It will be harmful for your reservoir directly. Okay. So, okay, the recovery rates can be combined. Okay, percent of oil recovered according to these three different drive mechanisms: solution gas drive, gas cap drive, and water drive. Okay, so initial reservoir pressures also you can see here, the compression. Okay, water drive can recover up to 70% of the oil in place. Okay, you can see up to 70%. A gas cap drive can recover only 40% with a greater reduction in pressure. You can see. A solution gas drive has the lowest recovery in here, as you can see. Okay, so in terms of structure, if I have a water drive, so I am lucky. We can say this one. Gas cap drive and solution gas drive shows a little less oil recovery for me. All right. So there are some other structures which shows the combination of all of these. Okay, in nature, you can see all of these in one case actually. So these called combination drive reservoirs. You can see, as in the figure, the gas cap is available, water is available also. Okay, so it has a solution gas as well inside your oil. So all three of these can be seen in one case. Okay, so here in the dry problems we mentioned already what's happening. As you can see here, there's a conic issue is happening. Conic issue is happening in here in the first one, and gas can also have conic issue in here. All right, gas conic issue can be here. So in water dry, water can cone upwards and be produced through the lower perforations. Exactly. So to prevent this one, what's happening if your water you are producing more than you expected, and it's not a desired thing, but you don't want to shut in your well. So there are with the technological developments, there are some devices used in downhole. So you are putting these devices, inflow control devices, according to, for example, in here, lower perforations. You are putting these and prevents your water come inside your inside your well bore. Okay, so these type of precautions can be taken as well. Gas cap also can have the same thing. In the gas solution drive, gas production can occur in the reservoir. It also resulted with skin damage. Of course, your well will be very short lived in this case. Okay, so these things we have to prevent actually. In the secondary recovery covers a range of techniques used to augment the natural drive of reservoir or boost production at a later stage in its life. A field often needs EOR techniques, enhanced oil recovery techniques, to maximize its production, of course. It's commonly applied in most of the reservoirs currently today. Common recovery methods are we talked water injection, gas injection, water alternating gas. In reservoirs containing heavy oil, other recovery methods are used to reduce the viscosity, such as steam flooding, steam-assisted gravity drainage, polymer injection, CO2 injection, puff and puff processes as well included to this. So these mostly used for heavy oil reservoirs. The aim is to separate the light particles of the oil from the tar and asphalting mass, all right, and produce the light particles. What I mean, light unproduced particles, we can say. It cannot be produced with natural methods, and you are using this and taking the light ones, and the asphaltene part and the very heavy ones remains as irreducible in your reservoir. It mainly use heating, actually. The steam and the others use heating, use heating. CO2 polymer injection use chemical, in chemical way it used. CO2 injection of also CO2 is used to remove these particles, to separate these particles from the heavy ones. Yeah, it's here two examples of this: the water injection and gas injection. We thought it's different than the previous case, right? So you are injecting directly. Here, for example, your gas injection, you are injecting through to your gas, the place that your gas cap will be naturally, all right? In the water, you are putting your water through to the place that your water has to be, but there is no water in there, okay? So these are two examples of water injection and gas injection. Of course, operationally, this is totally different, and have for the production, it has different parameters need to be evaluated. So this is the end of the first week. Next week, we will talk about the phase diagrams and the fluid properties. Thank you very much. Thank you very much for your listening. And if you have questions now, I would like to, I will be happy to answer you.
Firstly, thank you very much for taking time and teaching to us. And we have two questions. Let me ask. A student asked that while water injection, does volume of water injected remains same at reservoir conditions? If not, have to.
Can you repeat again, please?
While water injection, does volume of water injected remains same at reservoir conditions? If not, have do we account for change or shrinkage in injected water volume?
Okay, when you are producing water, you have to consider that your water has gas inside. In reservoir conditions, it's solution gas it has, but when it comes through to the upper parts, what happens? Your pressure and temperature decrease, right? When your pressure and temperature decrease, so the gas phase start to expand and form a solution gas, right? As a separate phase. But in the injection part, you are already injecting your water directly as a water phase, okay? So when it comes to the lower part, your pressure increase, your temperature increase, right? So it's expected not to have any gas phase in your reservoir, which source from your injected water. If you are injected for water, no. But if you are injected carbon dioxide, for example, so carbon dioxide is totally different issue. So you have to consider your carbon dioxide is in supercritical conditions you are injecting or not. If it will remain, if you inject it in supercritical conditions, it will remain as supercritical in the lower part or not. Okay, so you have to consider all of these. So for water, this is not a issue. This is not a big issue. No problem. But you are talking about other type of fluids, okay? It will definitely create some problem. So you have to consider in this case, you have to use your phase diagrams. You have to describe your pressure, temperature, and your fluid, the place of your fluid in that phase diagram exactly. How much % of that will pass to another phase or how much will not. You have to consider this in a very strong calculations. Okay, this is what I can say.
Thank you for answering. Second question, how to identify whether water drive is bottom drive or edge drive?
You can use core samples for this one. Okay, you can use the properties. For example, when I take a in situ core sample, okay, when I take a in situ core sample, I can directly say this is. Let me start with saying this one. Okay, all the rocks in the beginning were water wet. Okay, all the rocks in the beginning were water wet. So you can directly say that core sample, that pores exposed to an oil or not, or how long. Okay, so if it exposed to the oil for a long time, you can understand it from its wetting behavior. If it not, or if it exposed a shorter time, you can also understand. If it is not even a shorter time, you can also understand that from the course directly. Okay, with your measurements. So to answer this question, I can say I can use cores, okay, core samples for this, not outcrops, in situ core samples. But for other ways, actually, I am not aware of that. Okay, but if it is edged or the bottom of your water oil contact, core samples directly can give that. I had done some experiments about that. Okay, that's what I can say.
I think question is finished. Thank you again, Mr. Hakan, for taking time for us. And
I am aware that these are the basic subjects, basic parameters, but for the topics of third and fourth week, these will be very useful. These need to be identified. Because of that, I wanted to include these specific basic terms in the beginning, and then we will continue in next weeks. Please follow the courses.
And thank you guys for joining. Also, students, very thankful for you. And guys, can we take an image of this meeting? If one suitable, open the camera. Please, Mr. Hakan, can you close your screen sharing?
Exactly. Sorry. All right.
It's okay. Thank you. Thank you so much.
Thank you.
You can leave, guys.
Thank you.
Thanks.
Welcome.